Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor Nadya Mason, who is a professor of physics at the University of Illinois at Urbana-Champaign, where she specializes in experimental studies of materials. Professor Mason's research focuses on the electronic properties of small-scale materials, such as nanoscale wires and atomically thin membranes. Her research is relevant to applications involving nanoscale and quantum computing elements. She currently serves as director of the Illinois Materials Research Science and Engineering Center, a multidisciplinary research and education center funded by the National Science Foundation. Welcome, Nadya.
Thank you. Glad to be here.
So you were part of a committee on frontiers of material science research,
Yes.
Where you looked at what has happened and where we are going. When I was in undergraduate school in India in mid-'80s, my advisor, I remember distinctly telling me that material science is where all the action is going to be for the next 50 years.
Right.
Even though I went to graduate school in engineering, I sort of left engineering a long time ago. So you have to keep me honest here as we go through this. Some of my memories may come back, but some may not.
Right.
And so the research report says that modern material science builds on knowledge from physics, chemistry, biology, mathematics, computer and data science, and engineering sciences to enable us to understand, control, and expand the material world.
Yes, absolutely.
And you say, although it is anchored in inquiry-based fundamental science, material research is strongly focused on discovering and producing reliable and economically viable materials, from superalloys to polymer composites that are used in a vast array of products essential to today's societies and economies. So this is not a topic, typically we think about, but there's so much that has been done last 50 years or so in the area of materials. And like you say, the interdisciplinary approach to it, especially more recently, computer science and data science, seem to have done very interesting things there. So I thought we can maybe go through some classes of materials, to kind of set the conversation. So the first one is metals.
Yes.
And you say powered in part by widespread efforts such as the Integrated Computational Materials Engineering, ICME, approach to materials development, the National Nanotechnology Initiative, and the Materials Genome Initiative.
Yes.
Metals research during the past decade has achieved numerous advances. So could you describe briefly, first of all, what's the National Nanotechnology Initiative and the Materials Genome Initiative?
Yeah, so the National Nanotechnology Initiative, I believe this was from 2001 under Clinton or something that it started. This was an initiative to, that's what it says, to focus on things at the very, very small scale. Yeah. So in the 80s, especially, and even in the 90s, there had been huge developments in imaging things that were very small. So if you think about it, our light has a wavelength in the hundreds of nanometers, right? Hundreds times 10 to the minus 9. Whereas when we talk about a nanometer, right, that's 1 nanometer. So you can't image things that are that small with light because light's too big. That makes sense, right? So in the 80s, things like scanning tunneling microscopes, scanning electron microscopes, using things like electrons to bounce off materials and recreate images that way, gave us new ways of looking at very small scale structures and determining the electronics of these very small scale structures and their behavior. And once we could image these and determine their electronics, then we could start making things small. And then there are also correspondingly innovations in fabricating things that were very, very small. And so once these two things came together, we realized, okay, things at the small scale can be made, they can be imaged, and they act differently. And so once we had all this access, there was a huge boom in trying to study things and see what new behaviors could be created at these small scales. And then also, taking something that was very small and putting a lot of them together to make a composite or larger materials, or including them in other materials to get some new behaviors entirely. So that was the idea behind the National Nanotechnology Initiative. And that lasted 10 or 20 years or something. I think it's not, it basically ended already, but that allowed us to make huge progress in new types of materials like carbon nanotubes and nanowires. Everything has nano in it, as you can see. Right. So that was one. The other is the Materials Genome Project. Was that the other? The Materials Genome Project is so you know what the sort of Human Genome Project is. Right. The Human Genome Project, the idea was to map every gene in the human body. Right. And that's a huge project. It takes a lot of time, a lot of effort. But the idea is that once you know all the combinations that are there, you can start pinpointing individual ones to try to figure out which ones are useful. Okay? And that's the exact same thing that we do with materials. The idea is if you can make a database that contains every possible material combination, and if it's a smart database, just like, in the same way that we know what, we can start figuring out what genes correspond to eye color or to certain illnesses. If we can start figuring out what material combinations correspond to high conductivity, to high thermal, excellent thermal properties, all these things, we can create equivalent materials genome where we can start predicting new combinations of materials that give us the properties that we desire.
So this high entropy alloys, multi-principal element alloys or complex concentrated alloys are composed of nearly equimolar concentrations of 5 or more metals that form extended solid solutions. So you could essentially now create custom solutions of metals, right?
Right.
And so that's the sort of the metal material genome kind of go into that, or how does it work?
Well, a lot of the okay, so there's a couple of things here. I mean, one is so I would say that both the nanotechnology side of it is that a lot of these alloys are created by understanding the nanocrystals and the grains and everything at the nanoscale in these things. And then things like materials genome, I think, is used, especially for systems like this, to try to predict and understand which combinations can lead to better properties, for sure. So there's always some experiment. There's always some just experimentation and knowledge of how things work. You have to have a starting point. Materials Genome Project isn't finished. This is very much an ongoing project. So, you can start from that, and you can start with whatever knowledge there is already about materials, and then try to tweak it to try to create things that stabilize at different temperatures and have different sorts of properties.
Right. So the recent advances in computational technologies, data science, artificial intelligence, and so on, are we to a point that once we have that raw material, that raw data, can we actually say these are the properties that we would like to have for an application, and let the machine sort of determine how that would work?
Well, that's the goal. That's the goal behind it. But just as with the human genome, there's complications. So even when you have the whole human genome, you can't predict what small changes will what will happen if you make a small change, right? Or what happens in any particular sequence. And for better or worse, materials are very much like that. You can say maybe this combination will be interesting, but does it matter if it's at a 1% combination? Add 1% of the element, or 20% of the element, Or, when you combine them, do they actually melt together, right? Materials also have all sorts of other properties. Are they miscible? Do they have different, will one of them crack? Is one of them brittle and the other one flexible? There's all sorts of other issues that come in, even with metals. Are there things that when you combine them, do they oxidize in a way that they're very air sensitive that you might not have predicted? These are things that you still have to worry about. So the Materials Genome Project, like the other project, any genome project, is really a tool that helps you with your starting point. It helps you limit the variables to know, to give you a better idea of where a good starting point is, that we're, so that the fundamental research can begin from a more and more effective and efficient place.
Right. Yeah, it's sort of changed, right? Now we can maybe predict what the properties might be for a combination, and then go look for manufacturability of that, right?
Right.
It never used to be like that, right? We manufacture something and then test it.
Right.
Now we could actually hypothesize and then try to manufacture it. So manufacturability now is more of a important game.
Yeah, I mean, you call it manufacturability, but it is also, if you think about it, it's also fundamental research, and just under there, because it does require a lot of knowledge and testing and understanding of the fundamentals of materials, even just to combine them. So I think that maybe there's a misconception that to make a new material, if I wanted to make steel or something, I would just take some iron and melt in some chrome or something, and and out pops steel. That doesn't work that way, right? You have to harden it. You have to melt it at a certain temperature. You have to, if you're not very, very careful with materials in terms of exactly what temperatures you raise and you cool them, exactly how you combine things, they can just shatter, for example. So there is, even in the so-called processing stage, there's a lot of fundamental physics and material science and chemistry that goes into that.
Yeah, that's interesting. I was just about to say, so the process, one would think, is an engineering problem. I was just going to say that can be solved mechanistically,
right?
But that's not the case, actually.
No.
You have fundamental research happening in there too.
Yeah, and that's why materials. I think the quote you started out with, I think, was really great. That talked about how there's a fundamental, materials research is a focus on fundamental research, but always with an eye toward what might be useful, what might be helpful, what might be interesting. Because there's so much fundamental research that needs to go on to create materials. But you're always pushing towards something that you hope isn't going to break the minute someone tries to use it.
Right. You talk about bulk metallic glasses as a class of compounds. What exactly is that?
Bulk metallic. This one isn't really my area
of. So they say that metallic glasses during the past decade have fostered their progression from a scientific curiosity into a variety of specialized commercial products. So bulk metallic glasses offer near net shape formability, potential improvements in corrosion resistance and useful strength and fracture toughness. So does it have anything to do with glass as we think about it, or it's something completely different?
Yeah, I mean, a glass, so it's an interesting idea. A glass is basically something that doesn't have a well-defined lattice structure.
Okay.
So this is why a metallic glass is something that's different from what you might expect. So a glass is something that, if you think of a crystal, think of a thing like sodium, right? The atoms are all in a very well-defined square lattice, basically, right? And so many materials, like metals that we think of, have very well-defined lattices. But a glass, on the other hand, you think of as something that the lattice is irregular, it's distorted. Okay, so that's why glasses can flow, because the atoms are not arranged in a regular way. But most glasses that we think of are insulators. They don't conduct electricity.
Right.
So a metallic glass is something that has become, more viable and even, become commercially viable in the past decade. These are materials that are like glasses in that they don't have the same sort of crystal properties, but they are conducting at the same time.
Okay.
So in this case, they what they do is they take something that would be a glass and have that would have a crystal, basically a crystal structure like a metal, and then by adjusting, they heat it and adjusting the rate at which they cool it, they allow it to to have
to
what they call an amorphous
Yeah.
structure, right? Not something that where everything is well defined, but have some sort of amorphous structure where it becomes like a glass, basically.
Yeah, that's so interesting. Yeah, so you're taking a different material and essentially kind of modifying it to have properties, in this case of metal,
Mm-hmm.
right? And so this is the sort of, there's a second category. You have ceramics, glasses, composites, and hybrid
But just to be
materials.
clear, I mean, these metallic glasses they're metal alloys, but where you affect the structure of them, right? If that makes sense. That's what I was saying. So it would be like taking gold or some composite like that, and then adjusting the way that it cools so that it becomes a solid, but not with the same crystal lattice that it would normally.
Okay.
If that makes sense. So it gives it different properties than it would normally have.
It gives it different properties. So, but they conduct electricity.
Yes, yeah. But they might be in some cases they can be their shapes can be adjusted, or they can have more strength or be tougher than other materials. So these are things that have just really been sort of invented in the past few years, and they're still coming up with uses of these. But again, I think it gives a great example of how materials that you might think are, people often think that there's a standard type of metal or there's a standard type of glass, and it turns out that by doing research on how to heat them and cool them rapidly, slowly, you can deform them in such ways that they become different types. They become different than what they were, with even improved properties.
Right. Now, what's the difference between ceramics and glasses? They kind of fit into one class of materials, or no?
Let's see. Ceramics are, yeah. You're pushing my knowledge of the thing. I guess ceramics are different. Are typically different types of materials, I would say.
Okay.
Right. I think that glass. They're similar to each other. I mean, generally, a ceramic will have a better defined crystal structure.
And I would imagine, neither conduct electricity, right?
The typical ones, yes, unless they call it a conducting glass.
Right.
But of course, I shouldn't say that. They can. I mean, okay, so they can conduct electricity. It's just, often you have things that are like oxide ceramics, which are generally insulating. There are conducting ceramics, and in fact, one of the most famous types of high temperature superconductors, which are perfect conductors of electricity, are ceramic materials.
Okay.
So it's, again, we're pushing between sort of what we are comfortable with in sort of everyday life, which are ceramic pottery and things like this.
Yeah, so they're sort of converging, right?
Yeah.
So these terms that we use, to kind of categorize materials, it may not work actually in a few years.
Yeah, that's right. I think that's maybe an important point to make, that that there's a lot to be learned at the cross section between different types of materials, right? Between ceramics and glasses and conductors and insulators. There's usually there's things at the edges that cross between them that have new opportunities for applications and for understanding the science of these. And I'm sorry if some of these I seem a little vague on things like ceramics and glasses, because it's interesting. This materials decadal study that you're kind of basing this discussion off is it's every 10 years. The Department of Energy and the National Science Foundation commission this survey to figure out what are the major advances in the past 10 years of materials research, and what are the sort of promising opportunities in the next 10 years of materials research. But materials research is a huge field, which, as you said, encompasses physics and chemistry and material science. And so, they put together a team of something like 25 experts from all these different fields to work on different sections of this document. And so my own specialties are the areas of superconductivity and low dimensional materials and topological materials, which are a little bit more on the physics side of these. Things like ceramics and glasses, I would say, are more classic material science focused areas. And then there's some areas like polymers, which are really, in the chemists work on that a lot. So, with everything, with specialties the way they are, I have a vague idea of what ceramics are, but it's not an area that as a physicist I've ever really researched in or worked on.
Yeah, it's amazing. All these areas are getting so complex in some ways
Mm-hmm.
and so varied that so like you said, physics, chemistry, biology all coming together. So there is some convergence happening
Mm-hmm.
in basic sciences, but on the same token, it's also getting highly specialized,
Mm-hmm.
right? So from an application standpoint, so quantum materials and strongly correlated systems,
Mm-hmm.
this is one of the sections, and this is where sort of you specialize as well,
Right.
right? And so what is quantum materials to start with?
Um, oh, this is so it's another. Unfortunately, it's another kind of vague term. I think that
Yeah.
we use quantum materials when we're talking about materials where um, the quantum properties of the atoms are important.
Okay.
So it's kind of weird because quantum properties are always important. In fact, in a metal, we talk about just the atomic wave functions overlapping
Yeah.
and allowing them, giving you a conduction band where everything conducts well. And all of that is fundamentally based on quantum mechanics.
Hmm.
But when we talk about the quantum properties, we're often talking about even the quantized energy levels matter, that there's discrete energy levels of the problem
Right.
that come into play somehow. And I'll give you an example of that would be a superconductor, which is a material that conducts perfectly, like I said. There's an energy scale where a system will be superconducting, but if you exceed that energy scale, it will no longer be that. Or even if you have a very thin material, there's an energy scale where it acts like it's basically two dimensionals.
Right.
But above that energy scale, it may not. So there's lots of you can they said quantum energy levels. Things are confined up until some energy scale. So once you start talking about those energy scales, we typically will start talking about quantum materials.
Okay. So superconductivity is basically something can conduct electricity without any resistance, and it used to be that we have to get close to absolute zero to observe this, right? Long time ago.
Mm-hmm.
And the things improved. I haven't been following this. Where are we in terms of, in the 80s, there were visions of room temperature superconductivity. Are we getting any close to that?
Well, unfortunately, the transition temperature of superconductivity hasn't gotten much higher in the past 30 years, really. But I think our understanding of these superconductors has increased immensely. It turns out they're very, very complicated. And these are sort of one of the original quantum materials because they're not just superconductors. They tend to have a lot of different properties. Many of them have magnetic properties or other the electrons form stripes or form other structures on their surface before they become superconducting. So all of these, there's been a lot of progress in understanding all of the different electronic behaviors of high temperature superconductors. And I think that these are fundamental. This is fundamental progress toward designing something that has a higher transition temperature. So we're not there yet, but there's been a lot of progress in the fundamental understanding.
So when you say high temperature superconductor, you mean something like 100 degree Kelvin or something like that? Or
yeah, I think, let's see. So the highest temperature is something
around.
something like 130 Kelvin or 150 Kelvin or something like that.
Okay.
Right, above liquid nitrogen temperatures.
Right. So
it's still cold, but it's not as cold as many of them had. The early ones have transition. The elements have transition temperatures of 4 Kelvin or something. So 100 Kelvin is pretty balmy, or 150 Kelvin is pretty balmy compared to that.
Right, but not good enough for any sort of conventional applications like electricity, for wires for electricity and things like that. Because we used to think that it is coming, right? Room temperature superconductivity is coming, in which case you can actually, I think you gain something like 30% in losses in transmission, if I remember correctly.
Yeah.
So that's a big deal in terms of electricity, but that is not there.
It's true. But I would just to add to that, though, I think one of the interesting things about fundamental science is that you never know what you're going to get instead. So, I think if we could find more energy efficient ways to transmit electricity, that would be hugely important for society and for our world. On the other hand, things like magnetic resonance imaging, MRIs, run on conventional superconductors. So an MRI has a superconducting magnet inside, which allows you to make a very, very large magnetic field for this imaging without overheating the wires. And these work perfectly well with conventional superconductors. Of course, would it be easier, it would be cheaper to have it without a superconducting magnet inside, or without the helium cool, these are cooled to 4 Kelvin or something. Without a helium cooled magnet would be easier. But even with a helium cooled magnet, these are impressive uses of superconductivity. I just want to add to that. The other thing is that I don't know if you've been following the quantum computing progress that's been made in the past few years.
Yeah.
But there's, again, in the past 10 years, there's just been tremendous progress in terms of making quantum computers. They went from something like, a couple bits to hundreds of bits, which is incredibly hard to do. No, I don't think many people were not sure they'd even get to this stage. But, the IBM computer and the Google computer are all based on superconductors.
Right.
And so even though we don't have power delivery to our houses with superconductors, our first quantum computers may well be with conventional superconductors.
So one other item here is two-dimensional quantum materials.
Yes.
So two-dimensional meaning it is just one atom thick.
Yes. So the materials that you're talking about here are atomically thin materials, and this is something that's really these are materials that have been discovered in the past 10 years, basically, 10, 15 years, and these have been probably one of the most exciting developments in material science is the discovery that something that's only 1 atom thick can be stabilized in air. Because if you think about it, that's so thin, right? I mean, you can already think of taking the thinnest material that you could imagine and holding it up. It would just crinkle. It would blow away. You couldn't hold it. It would tear, right? There's so many reasons to think that this couldn't exist. And yet it was discovered that you could just lay this out flat on a little substrate and there'd be an atom thin layer of material that you could put contacts on and study, that you could shine light on, that you could image, all sorts of things and all sorts of new behaviors.
Is it transparent?
Yes, it is. It is. So the first material like this to be discovered was graphene. This is carbon in a lattice structure that's just 1 atom thick on a surface. And graphene has many, many amazing properties, including being transparent. So it's very strong, highly conductive electrically, and also transparent. So very interesting for transparent material applications.
Right.
But since the discovery of graphene, there's been a discovery of many, many, many more types of materials that can be made just 1 atom thick and have also all sorts of unique properties. And so there's just been a boom in our ability to create, understand, and manipulate these purely 2D materials.
And in some of these, I don't know the technical basis for this, Nadya, but topological materials.
Yeah.
So you sort of get some sort of superconductivity on the edges or something like
that? Some conductivity, yeah. Topological materials are another thing that's just been studied, that's been discovered in the past 10 years. This is a rare case where these were predicted theoretically before they're discovered experimentally. And predicted just someone looked at the electronic structure of it and said, if you have this material, the electronic structure should be inverted in this way, where instead of having just a standard insulating material, you should get an insulating material that on the inside, but has conducting surfaces on the outside, which is really crazy when you think about it, right? I mean, what would make a material, how does it even know where the edges are or anything? And that's what tells you that there's something really crazy quantum mechanical about this. Go on.
And so one of the applications of that is in transistors, right? Is it?
Possibly, yeah. So these conducting surfaces tend to have very low power dissipation. And they can transfer spin. They can transfer a quantum mechanical property of electrons called spin rather than charge, preferentially. So that is also uses less energy and can move things without heating. So they could be used for interconnects, possibly. They can be used for specialized type of transistors, on-off switches, for different types of inductors, possibly. And it's interesting. These are, so these quantum materials are the things that we do in my lab that we do research on. So I do a lot of superconductivity, and I do a lot of superconductors connected to these topological materials. So we found, for example, that when you put a superconductor on a topological material, that the superconductivity only flows through the surface of it. right? Even though there's a whole interior, you get almost all the superconductivity just on the surface flowing around the outside of this thing. So you can see, and this again is a new way of maybe having an efficient transfer of superconductivity. So you find really interesting behaviors when studying these.
Yeah, so the battle on computing, as you know, is moving toward power consumption.
Yes.
I think all this data centers, I think is consuming something like 30% of all the power produced in the world. So they're setting this up in Scandinavia because northern Sweden and Finland and all of that, because cooling these things down is another big problem.
Yeah, that's right.
For data centers,
that's right.
And so these things presumably will have applications in that area.
Yes, of course. Yeah, absolutely. So lower power devices is huge. So things like topological materials that have surface states or edge states that can conduct without dissipating power are incredibly important. Superconductors, of course, don't dissipate powers. They're incredibly important. And then things like graphene, the other things like graphene are also, they can dissipate power, but they could also be made very, very small and still conduct in ways that other materials can't. I should mention that, one of the interesting things, it is of course for applications that we know, but one of the goals, for example, in my group and other groups of looking at these materials is for thinking of just new behavior. What about applications we haven't thought of yet?
Yeah.
So we do things like we put magnets on topological materials and see how the current is varied, or connect, or look at graphene and see if we can induce, if we can modify the surface, if we can put it on a nanostructure, the surface, in such a way that we can control its electronic properties in a way that hasn't been done before. If we modify, if we induce changes on the surface of graphene, can we get edge states that didn't exist before? And so these are sometimes, yes, in the long run, we're looking for applications like less power, higher switchability, all these things. But also, is there a new behavior? In topological materials, the electric and magnetic fields are connected in a way that's not seen in almost any other material. Can you have a new type of electromagnetic switch that you didn't even know about before? This is not possible.
Do you see possibilities, Nadia, for levitation? I know that the levitating trains use superconductivity, right?
Right. Some of them do. Yeah, it's possible. It is possible. I think, again, I think there's some people have moved away from that a little bit, because that would require, if we did find high temperature superconductivity, that might be efficient, right? It might not be efficient, right?
But the topological materials, I wondered, it's such a weird thing, right? And power flows on the edges only in one direction too, right?
Yeah, that's right. Power only flows in one direction on the thing. Yes.
And so I wondered, I know nothing about this, but I wondered, combining different topological materials, if you can get some sort of magnetic levitation at no cost.
I'd probably stick with superconductors about for magnetic levitation. I think you get other things out of topological materials. I think, when I think about materials, it's interesting because, of course, I work on materials, but I work on the physics side of materials. I think about their fundamental properties. And I think it's really important to keep in mind that we're really exploring nature in the same way that people look at the sky and wonder, what's out there? What does it mean? How did those stars get there? What are they made of? They're not asking because they think there's an application. Although, yes, it may be nice to go to the moon or to Mars or something like that. They're asking because they have curiosity. And out of that curiosity comes knowledge plus applications like GPSs, right, that rely on general relativity and things. So materials are very similar, although we often will think of materials as very practical because, of course, it's what we use all the time for every device and everything we touch as a material. On the other hand, I think that by looking at these things, there's a huge exploration aspect of what can we find? What is different in these things? What can we imagine and see that we couldn't imagine and see before? Right. And out of that comes entirely new behaviors and even new applications.
Right.
So, yeah.
Yeah, and the 3D printing revolution.
Oh, huge!
Gives it a new meaning too, right?
It does.
You got to feed the feed the 3D printer in the future?
Yeah, so 3D printing adds I would say, a more practical aspect to it, which is we've just talked about how materials genome, and there's different combinations of materials that give you different properties, and we're figuring out more and more about these all the time. Mm-hmm. And what a 3D printer does is it gives you the opportunity to make immediate changes, right? To make the thing you need in real time, even if you're out in the field or in a school or in the office or on a battle zone or anywhere you are. You can make something specific for your needs just by combining materials. It's like, right. The best, the dream in some sense of materials applications would be combining the materials genome with 3D printing. Mm-hmm. So you come up with something and then you just make it. We're not there yet, but it's an exciting dream, I think.
Yeah, it's also, in some areas, generally humans have a prescriptive way of experimenting. And oftentimes, if you have a design space and you're searching that design space to find something, sometimes it tends to be inefficient because we bring a lot of biases into it. Mm-hmm. And so one direction artificial intelligence is to say, let the machine experiment and let it guide the search of the design space to find something. Mm-hmm. And I wondered, if there are things like that you are doing in material sciences arena. So what I mean, Nadya, is, mm-hmm. Let's say you have an objective function. You want a material of these properties, mm-hmm. and humans could go into the lab and they could experiment. They could do different things using their intuition and experience and knowledge. Alternately, you can basically let the machine run those experiments and learn from those experiments and redo those experiments, right, in some way.
Right.
In biological sciences, for example, these types of things appear to have more power. Part of that is because of the biases, people bring to the process.
Mm-hmm. Mm-hmm. Yeah, no, I mean, I think again, it'd be incredibly useful if we could do that. And there's a lot, and there is, like I said, the materials genome, part of the materials genome project is trying to do things like this. I mean, people will make what we call an evaporator, which means that they put, they can put up to like 50 or 60 materials inside a system. And then they can heat the materials so that they evaporate, meaning that they can go onto another substrate. And they can make, up to 60 combinations of materials in situ, for example.
Right. Right.
So, you can have a machine make, and people are trying to have, people make machines where they do this, they make gradations where you have different combinations of the same materials and all the time, and then you can automatically test it for different things. I think that there's a space for this, and it's incredibly interesting. The problem is that, as I mentioned, there's still too many variables to make it useful all the time.
Yeah.
So, let's say you put 60 materials in there, and then you have 60 to the 60 combinations of materials. Right. And then you have to test these 60 to 60, but what are you testing them for? Right. Are you testing them for thermal properties? Are you testing them for electric properties? Are you testing them to see if they're topological? There's lots of things that, this is a tool, but just one. I would say another tool that's been invented recently is a more analytic way of predicting, for example, whether things are topological or not, right? This is one of the huge advances in the field is that there's a way of actually looking at the crystalline structure of known materials and then predicting them to have specific topological properties. And this is something that I think that combined with a genome project, using an analytical calculation or understanding of the way materials are and their structures, and then categorizing them according to, these have good thermal properties, these have good electric properties, combining that with some machine learning and some materials genome, those combined have, I think, a lot of promise.
Could be very powerful. Yes, I just want to, so that these topological materials, when they superconduct.
Yes, go on. Yes.
So when it superconducts, it's doing that in room temperature?
So the topological materials aren't what we call superconductors intrinsically necessarily. Okay. Not all of them. They're just conductors.
Okay, but it does get some sort of superconducting ring around it, right? So
no, they just get a conducting ring around them,
okay,
not a superconducting. Now, some of them do happen to be superconductors, and you can connect them to superconductors. And a superconducting topological system is useful for different sorts of quantum computing schemes, for example. So that's a whole other area. We're also looking at we do a lot of coupling superconductors to topological systems in my lab. But no, the conducting surfaces are just conductive. They're metallic conducting surfaces, not superconducting surfaces. Okay. And the difference is that a metallic system, there's a like I said, a superconductor is a quantum mechanical ground state, meaning that there's an energy gap to becoming a superconductor, and you don't have these in the topological system. It's not a superconducting energy gap. It's maybe a topological energy gap, but not a superconducting one.
Right. I don't know if there's any connection, Nadya. I just want to ask you. So, this cognitive computing arena, one of the things that that seems to be interesting is this memristor, right? So, I wondered if any applications that you have looked at for memristors in this arena.
I haven't particularly looked at memristors, but I think people are looking at these as for neural networks and things. I thought, isn't that right?
Yeah. So the issue in artificial intelligence is that almost all of it is driven by software today, and we're going to hit some kind of a constraint on the software side. So one idea is to actually have hardware. So it is something that can memorize and compute at the same location, just like a neuron does in the brain. And so I don't know. I mean, there might be some applications here as well.
Sure. I mean, my understanding of a memristor is that of these neural networks is that they're basically trying to reproduce the behavior of neurons.
Yeah.
Neurons are things that fire in short pulses. Right, and that have memories of each other. Right, if one fires, another fires, for example, and they know that the length and duration of each other's firing. And so there's a very specific behavior of neurons. Like I said, these quick pulses that have relationships to each other that you can mimic with certain types of devices. Right, so if you can create something that has a blip like that, that's that can be turned on and off in a very specific way with a voltage, and that can connect to another one of these devices, then you can mimic a neuron. And memristors are basically things that can be used like this to mimic neurons. And the idea is once you can start mimicking neurons, right, then you can start feeding it information and seeing how it behaves in the same way that neurons behave.
Yeah, so what the beauty of neuron is that it's actually memorizing and computing. So compute and memory are co-located.
Right.
And so that is,
that's what I was saying. That they remember. They have. That's what I say about a connection to other neurons. They know when they've fired, and they know when other things have fired, basically, right? But they also can fire independently. But I guess what I'm saying is that it's not, these devices in and of themselves are. I wouldn't say that they're a revolutionary in and of themselves. But there is some potential opportunity there in getting them to mimic actual neural circuits and mimic neurons.
Right. Yeah, and there is enough to learn inside the brain. I think that'll keep us occupied for a long time.
Yeah. So I don't know. So is your question? Are we going to come up with new materials like this that can mimic the brain? Is there a connection between materials and biology? All these things, and the answer is yes. I think that there's always going to be a connection, that people will find analogies between brains and electronic devices. I think there's my guess is that there will be a great advance when we have our first quantum computers, which can solve problems in parallel in the way that that they may be able to mimic brains better or even improve on them by doing this massively parallel processing that founds these lowest energy states. But yes, all of these things are dependent at the end of the day on materials advances. Yeah,
it depends on material. So I think it is true that this is where most of the action is going to be, in the sense that if you want to advance computing, we have to look back into hardware,
Yeah.
into materials.
Yeah.
I think software is going to run out of steam
Yeah.
if it hasn't already, right? So that's where the connection is. I want to also touch very quickly, Nadya, on this bio-inspired materials. Is that an area that you can talk about?
Oh, I haven't worked on those very much at all.
Okay.
I think I know a little bit about it. I think it's extremely, I don't have any details, but it's an extremely interesting idea, of course. And it is what it says, right? You look at a butterfly wing and see what the lattice structure of those butterfly wings are, and then try to recreate that in a different sort of material, an artificial material. And of course, it's, they've seen artificial shark skin, right? Sharks can, the water just kind of shears off of sharks, and you can make an artificial shark skin in a wetsuit that does a similar thing. There's all sorts of things like this, and I think we have a lot to learn from biology. Again, we're dealing with a space, material space that's enormous, right? If we just try to just combine everything blindly, we have the age of the universe combination that we can possibly make. And so this is why I keep saying, if we use all the tools available to us, which includes some machine learning, some other things, and looking at what exists, I think looking and seeing what exists in biology and how, billions of years of genetics have managed to solve some problems is a tool that we should and can use.
Right. Yeah, I think we touched on this already. So on the process side, simulation and computation tools, those things are improving. So integrated computational materials engineering and materials genome initiatives, we talked about that. Computational materials science and engineering, machine learning and materials discovery. These are things that we would not have talked about even 10, 15 years ago.
No, not at all.
And so the field is sort of fundamentally changing.
Yeah.
Part of the remit of this committee that looked into both history and looking forward is sort of assessing how competitive we are in this arena, right? What is your sense? Are we ahead? What are other countries doing in this area?
Yeah, I don't know if I want to comment if we're ahead or not, but I would say that other countries are either catching up, have caught up, or have jumped ahead. There's the problem with materials studies, including devices and including fundamental materials studies, is that they don't seem as exciting to people sometimes. I mean, funding agency, the public, it's just a material. Who cares?
Right.
And it can be slow, right? People have to spend a lot. Like I said, there's a lot of grunt work there of just figuring out what temperature things combine and what happens as you cool something slowly. And there's a lot of failures in there. You can spend years just trying to make one new material and then it never works. Right. And so you have to actually invest a lot of resources, personnel, time, and effort into making new things. And unfortunately, in the US, the way that the budget structure, the grant structure, the reward structure is set up, it's not set up to reward that sort of slow investment.
Right.
So what happened was that there was less and less money put into materials infrastructure, into hiring material scientists, into hiring physicists who looked at materials just to do fundamental studies, whereas other countries like China and Japan spent a lot of time and money in building up their materials infrastructure.
Right.
And so for the past 10 years, you've started to see a lot more new materials be discovered in China, for example, because it's building that system I said that has 62 elements inside that can evaporate, that can make different combinations of materials. That thing costs several $1 million. It's not the sort of thing you can just build in your basement. Someone has to invest in it. The government has to invest at the highest level in these things. Right. So I think that we've not invested enough materials, and there's been recognition of this at the top. There have been, the National Science Foundation, for example, has started some new materials initiatives. There have been some private foundations like the Moore Foundation, which have started investing in materials people. But we just need more. I think at the end of the day, the materials are the basis of so much of what we do. And again, just the fundamental nitty gritty, how do these materials combine part of it, rather than the most exciting, I discovered a whole new material and field. It has to be supported. You have to support both sides of that.
Right.
And we need to do more. Yeah.
And what's the intellectual property patenting status? so suppose you come up with a new process, suppose you come up with a new combination, are those things patentable?
Yeah, they are. Of course
Okay.
they are. Yes.
And so if we just sort of look at the cross-sectional, number of patents coming out of countries, is the US competitive in number of patents?
This I don't know. I'd have to look
Okay.
this up. Yeah, sorry.
Yeah, I mean, that would be interesting. It's one output that we can see, right?
Yeah.
And that sort of includes what universities are doing, what the government is doing strategically in this area. It's a very difficult thing, like you say, because it's a long cycle investment and a long cycle return problem, right? And so you can imagine countries like Japan really doing well in this area because they seem to have longer horizons.
Right. But even the European Union does. I mean, that's the crazy thing, is that even the European Union will invest a lot of money in big centers for materials, for example, right? They have a huge center in graphene, and they have huge centers in magnetics, for example. It requires a high-level government investment that other countries will make.
And most students need to get into it. So you have to sort of make this field more sexy, I guess.
Right, exactly.
Yeah, so there was a Nobel Prize 2016 or something in the materials arena. Was there?
Was that, I don't know.
There was some
so I mean, graphene won the Nobel Prize in 2005, I think.
2005. Yeah, there was something in 2016. I can't quite remember. That was also, I thought.
I'm sorry, 2010 was the graphene Nobel Prize.
Okay.
2016 Nobel. I'm curious what that is.
Because those types of things help, right? To sort of showcase the industry.
Oh, of course. The 2016 Nobel Prize was the Kosterlitz-Haldane. This was for topology of materials. Interestingly, this was so Duncan Haldane, kind of they're all theoreticians, and he did the theoretical basis of a lot of topology. But Kosterlitz and Thouless worked on two-dimensional superconductors, which to me is especially interesting because it was a topic that I'd worked on for my thesis project, looking at transitions that two-dimensional superconductors make between superconducting and insulating states. And they discovered that these transitions that they make were due to, could be described by the topology, basically. It's hard to describe, but anyway, they discovered that it wasn't a simple electronic structure. It was sort of a meta way of describing it. And they won a Nobel Prize for this because that paved the way for this field of topological behavior that we talk about now. And so, yes, that's sort of that was based on materials. I mean, when we say materials, this is condensed matter physics, right? They are condensed matter physicists. We say condensed matter because all materials that's not gas or liquids or single particles is condensed matter. But there have been a lot of condensed matter physics Nobel Prizes. It's just that historically they haven't gone to the people who make the materials. And in fact, there's a very famous case that there were 2 awards for quantum Hall effect. This is an effect. This is really the first topological effect that was discovered. So I'm trying to think of when the quantum Hall effect Nobel. So the Nobel Prize was given in 1985 for this material, but it wasn't given to the person who grew the materials. Right?
That is engineering.
Yeah, exactly. Exactly. Yeah. So, and saying actually, I'm actually thinking of the fractional quantum Hall effect. This was the one. So there's a quantum Hall effect, which is just a standard material, and then there's a much more sort of specialized case of this, where there is what we call the fractional quantum Hall effect, where you see these dips at these fractions of conductance, and that was something that was enabled only because a material, gallium arsenide, a certain type of semiconductor, was made extremely pure. But the person who made this material was cut out of the prize. And the people who just measured the material or predicted the material were given the prize. And so this is the sort of thing, that's the sort of thing that we have to stop, right? The people who enable it and make these things are as important as the ones who measure it.
Right. Yeah, so in conclusion, Nadya, if you look forward 5 years, let's say, where do you think we will make the biggest leaps in material sciences and material sciences research in general?
Yeah, I mean, materials, condensed matter physics, material science. I think I think that there's two. I think there will be progress with combining machine learning with existing knowledge, especially if we combine machine learning with things like metadata, how things are made, temperatures, all this. If you can figure out a way of putting metadata into machine learning in the next 5 years, that could be transformational, because it changes something that is drudgery of trying everything to being able to try to make new materials with a very efficient and good starting point, which would make it much more appealing to people, I think.
Make it much more appealing, so you can delegate a lot of the mechanics to the machine.
Yeah, exactly. So you can do the drudge work of just trying all sorts of things, so you hit upon something interesting, might be taken care of computationally, and then when you start, you can deal with how do you optimize it. Do you see these behaviors? You can start getting to the more interesting things to work on. Right. So that's one I think could be huge. Well, I'll leave it at that. That's an area that could transform condensed matter physics and materials research.
Excellent. Yeah, this has been great, Nadya. Thanks so much for spending time with me.
You're welcome. It was my pleasure.
And, good luck with your research.
Thanks very much.
Thank you.
Take care. Bye-bye.
Bye.